So for this one, here's the free body diagram. And all the stuff that appeared with no friction still is in there. So there's still 147.15 down. Still a normal force. Tension force of 200. But now there's also a friction force. Which direction is it going? Yep, it's going opposite the motion, opposite the velocity vector. And that's going to be equal to 0.2 n. And so Newton's second law says if we use a coordinate system rotated like this, 200, 0 plus that weight force is going to be the same as it was before. What are the components of the weight force? Yeah, and what do you have the components? 94.59?
Yeah.
Okay.
And then negative 122.
72? Point 112? Okay. Negative 112 point what? Okay. And then there's the normal force. And then what are the components of the friction force? Yeah. I knew you knew it. Okay. And those are equal to the mass, 15, times the acceleration, a0. So this time, now that there's friction, we can't just ignore one of the two equations and solve for the acceleration. We have to first solve for the normal force using the y equation, then plug that answer into the x equation. So we have the second equation says the normal force is equal to 112.72. The x equation says, what was that, 105.41 minus 0.2 n, and we know what that n is, 0.2 times 112.72 is equal to 15a. So can someone calculate this? What do you get from this equation? What's 0.2 times 112? Minus 22.54. And so, what's this? 82.87 is equal to 15a. So what do you get for a? 5.53? Okay, meters per second squared. So the acceleration vector is positive 5.52 meters per second squared, 0. So with no friction, we had an acceleration up the ramp of 7, okay? With this amount of friction, we had a smaller acceleration up the ramp. So now if we change the direction, do you have any intuition about what's going to happen to the acceleration? So say we keep the same coefficient of friction, everything like that. What do you think is going to happen to the acceleration when we just change the direction of motion? Like, will it affect anything? I mean, so without friction, it didn't affect anything, right? That never even comes up, right? The acceleration, and that's what I was sort of trying to get at when I was talking about if it's going this way, it means it's slowing down. If if the velocity is this way, it means it's speeding up. But the acceleration is the same no matter what. But with friction, it actually matters because it's changing the direction of a force when you change the direction of the motion, okay? So in the example we just did, where the motion was up the ramp, was that right? Up. That creates a force going down the ramp, okay? If we switch the direction so the velocity is down the ramp, it's going to create a force going up the ramp. And so what we should see is actually a bigger acceleration value up the ramp than we had before.
Didn't you say, I thought you said in class that for this, like, friction to speed something up would be against the direction.
Yeah, it never speeds anything up. The friction is always going in the opposite direction of the velocity.
Oh, velocity, okay.
Yep. But acceleration, yeah, it can. Okay, so now, part C, say that it's sliding down the ramp. Say that we still have the same coefficient of friction of 0.2. And calculate the acceleration vector.